Engine stalling at idle is a frustrating problem that affects many vehicles. When your engine runs fine while driving but suddenly dies when you come to a stop, specific systems in your engine are failing to maintain the delicate balance needed for smooth idle operation. Modern engines are designed to maintain a steady idle speed between 600 and 800 RPM. This precise control is managed by advanced engine control units that constantly adjust air, fuel, and ignition timing. When stalling occurs, the RPM drops rapidly below the minimum threshold, causing the engine to shut off. However, because the underlying systems can still function, the engine typically restarts without issue. Idle stalling typically stems from problems in three critical engine systems. The air and fuel system controls the combustible mixture, the ignition system provides the spark, and the idle control system maintains proper airflow at low speeds. The mass airflow sensor measures incoming air and tells the engine control unit how much fuel to inject. When this sensor becomes contaminated with oil, dirt, or debris, it sends incorrect readings, causing the engine to receive too much or too little fuel at idle. Vacuum leaks in the intake manifold or connecting hoses allow unmetered air to enter the engine. This extra air leans out the fuel mixture, making it difficult for the engine to maintain stable combustion at idle speeds. The idle air control valve bypasses the closed throttle plate to provide the precise amount of air needed for idle. When this valve becomes stuck, dirty, or fails electronically, the engine cannot maintain the correct air-fuel ratio at idle. Direct injection engines are particularly susceptible to carbon buildup on intake valves. Unlike port injection systems, direct injection provides no fuel wash over the valves. This carbon accumulation restricts airflow and creates turbulence that destabilizes idle operation. Modern engines are precision instruments that operate with much tighter tolerances than older vehicles. Minor contamination or component wear that wouldn't have affected previous generations can now cause significant idle stability issues. Understanding these systems helps you identify problems early and maintain smooth engine operation. Diagnosing idle stalling requires a systematic approach. We start with the most basic checks and progress to advanced testing methods. First, check for diagnostic trouble codes using an OBD scanner. Monitor live data streams while the engine is idling to identify patterns and anomalies. Next, perform fuel pressure testing. Normal fuel pressure should be between 30 to 80 psi depending on the system. Low pressure indicates fuel pump or filter issues. Compression testing reveals engine mechanical condition. All cylinders should be within 10% of each other, typically between 120 to 180 psi. Ignition system analysis using an oscilloscope reveals spark quality and timing issues. Look for consistent firing patterns and proper voltage levels. For vacuum leaks, smoke testing is highly effective. The smoke machine pressurizes the intake system, making even small leaks visible. Carbon buildup on intake valves is common in direct injection engines. Walnut shell blasting effectively removes deposits without damaging valve surfaces. Regular maintenance prevents most idle stalling issues. Clean fuel injectors and throttle bodies every 30,000 miles. Replace air filters regularly and use quality fuel with detergent additives.